At 2 a.m. in London, this building looks like any other office block, but a thermal analysis of the structure reveals a different reality, a facility operating at the edge of physical failure, moments before a catastrophic collapse. The hardware density is extreme. The floor is packed with 120 kilowatt racks of NVIDIA Blackwell clusters, each generating 1,200 watts of heat. Engineering principles define these facilities as energy conversion buildings. Electricity goes in, computing work is performed, and nearly all of that energy is expelled as heat. But the operators ignored the environmental data. Despite a forecast of 41 degrees Celsius, they opted for green airside economization, pulling outside air into the facility to avoid the high electricity costs of mechanical chillers. Prioritizing cost savings over the physical cooling requirements of the hardware removed the facility's thermal safety margin. The disaster was a design choice. The server floor is mapped into intake cold aisles and exhaust hot aisles. In this layout, power distribution units are mounted at the rear of the racks, positioning them within the high-temperature exhaust stream. Over the last decade, server efficiency algorithms have increased exhaust temperatures by nearly 10 degrees Celsius, flooding these hot aisles with intense heat. To maximize floor space, engineers placed critical infrastructure, like UPS batteries, directly in these exhaust paths. For many months, constant exposure to these elevated temperatures silently degraded the chemical components of the power systems. The facility effectively dismantled its own life support system. The power infrastructure was crippled long before the heat wave tested it. The cooling design relied on a redundancy fallacy. While there were multiple backup units, they were all routed through a single shared coolant manifold pipe. When ambient air reached 41 degrees, the mechanical stall began. The rooftop heat exchangers became completely unable to reject heat into the superheated outside atmosphere. Inside the servers, the internal cooling loop spiked to 62 degrees. This exceeded the 60-degree boiling point of the dielectric fluid inside the pipes. This triggered cavitation. The fluid began micro-boiling inside the pumps, turning the liquid into a froth of gas bubbles that the blades couldn't move. The mechanical impact was immediate. Coolant flow dropped by 90% in just 12 seconds. The liquid cooling system was strangled by its own physics. The shared manifold meant that when the pressure dropped, every redundant unit failed simultaneously. The monitoring software was the next failure point. To save processing bandwidth, the management system pulled temperatures only every 5 seconds. In thermal runaway, silicon heats up 15 degrees per second. This 5-second gap allows hardware to melt before alarms trigger. Boiled fluid forms a vapor blanket over the GPU die, trapping 1,200 watts of energy directly inside the silicon. By the time the emergency power off triggered, the GPUs were already destroyed. The degraded UPS batteries buckled under the load, failing to provide the clean shutdown required to save the data. The physical destruction was total. GPUs reached 145 degrees Celsius, causing the circuit board layers to delaminate and warp permanently. The abrupt power cut caused a massive right-hole error in the storage arrays. Generators could not synchronize with the unstable frequency of the failing UPS systems, leading to cascading data corruption. Over 4 petabytes of banking data were corrupted. The London Stock Exchange workspace crashed, and the FTSE 100 dropped 50 points at the open. Insurance providers triggered the force majeure clause to avoid the $400 million payout. Their investigation cited a gap between the facility's 1 in 50-year cooling rating and the 1 in 100-year severity of the 2026 heat wave. The $400 million loss resulted from an under-engineered safety net that was mathematically guaranteed to fail in these conditions. This wasn't an isolated failure. The same engineering models and cooling designs used in this facility are standard across the global digital infrastructure. The industry is facing a contradiction. The race to deploy extreme density AI chips while simultaneously pushing for higher operating temperatures to reduce energy costs. Operating critical power infrastructure at its thermal limits ensures that fail-safes will break exactly when they are needed most. Energy efficiency is a thermodynamic illusion if it destroys the power infrastructure keeping the servers alive. The pursuit of density without thermal respect is simply a countdown to the next collapse.